Okay, so the first speaker is Miguel Anjos, École Polytechnique in Montreal, which is towards efficient higher order semi-definite relaxations for max cut.
Thank you, Murray. Well, I want to start by thanking the organizers for giving me the opportunity to attend the workshop and the rest of the program, and also for giving me the opportunity to present. I'm going to talk about what we call higher order semi-definite relaxations for max cut, and this talk is really about efficiency. So we're looking at how to compute tight bounds on max cut problems computationally more efficiently. Okay, we're talking about computational efficiency in this talk. This is joint work with three co-authors: Elspeth Adams, who's my PhD student at Polytechnique, Franz Rendel and Angelika Wiegeler, who are at Klagenfurt, and two of my co-authors are here. So also, if perchance I don't know the answer to any of your questions, I can deflect it to one of them, and hopefully we can answer all your queries that way. I'm going to start by introducing the max cut problem. It's already been mentioned, in particular in the talk by Manuel Candes. I'm going to introduce it in a different way because I'm going to go through the graph definition in detail. So the idea is we have a graph with vertices and edges. We have n, which is the number of nodes or vertices in the graph. And we have weights on each edge, wij. And the idea is to find an edge cut of maximum weight. So we're going to divide the set of nodes into two parts, which I can call left and right. And I'm going to count the weight of an edge if its endpoints are on different sides of this partition. Okay. And I want to find the partition that maximizes the total sum of the weights of these edges that are cut. We're going to assume that there's no loops and that the graph is complete, so that if some edge is not present, we just put a weight of 0, which means it doesn't have any impact in the solution. And now I'm going to represent a cut in this graph by using a vector x, which has n entries, each of which is +1 or -1. And these represent whether the node is on the left side or the right side, whichever way you want to think about it. They're the two sides of the partition. And using this vector x, I can now formulate my problem in this way. So I'm going to maximize the sum over all the edges of the weight on that edge times this function here. And this function here has the product of xi and xj, which are the endpoints of my edge. So if the endpoints are in different sets of the partition, this gives me a -1. The whole function gives me a 1, and I count that weight. Otherwise, if they're on the same side, this gives me this gives me a 1, and then this gives me a 0, and I don't count that weight. Okay. So this is counting the weights of the edges that are cut. The constraint that I have is that the x's should be +or -1, so that's a nice quadratic constraint. This gives me a quadratic objective on x, quadratic constraints on x, so it fits the theme of the workshop being about polynomial optimization. And what I'm going to do also here is I'm going to rewrite this objective function simply as x transpose qx, which up to a constant has all the information there, where the matrix Q is defined in this way based on the matrix of weights. Okay. So max cut, another way of looking at it, is that we're maximizing a quadratic function over the set of binary values for the elements of the vector x. And this is known to be an NP-hard problem in general, although some instances are easier. And I'm going to also use Z max cut to denote the optimal value of the max cut problem itself. To get a semi-definite relaxation, I'm going to make a change of variable. I'm going to have this matrix big X, which is little x transpose. X is + or -1s. And then using this standard approach in the area, I can linearize the objective function as the inner product of q and x. And I have these constraints that we already saw, that the diagonal of x is 1s, the rank of x is 1, and that x is positive semi-definite. And if I could solve this, then I could solve max cut. But what I've done is I've put all the difficulty in the rank constraint. If I remove the rank constraint, I get the basic semi-definite relaxation for the problem. Okay. And this z SDP gives me a bound. that's one relaxation. In a sense, what I really would like is this ideal relaxation, which is the convex hull of all the feasible solutions for max cut. Okay? So if I take these 2 to the n minus 1 matrices of this form, okay, I can think of them as points in this matrix space, and I can take the convex hull of them. Okay. This would be perfect for me because I'm optimizing a linear function. So if I can optimize over this set, I'm going to get the exact value for max cut. Okay. Difficulty is that we don't have in general representation for this object. So I can formulate it as maximizing over this polynomial. But what I do know is that it's contained, that's basically what I've already shown, it's contained in the set of correlation matrices, which is the feasible set of my SDP relaxation. So by optimizing over this set that I can describe, I get an upper bound. Now the question is, how good is this bound? And that's already been studied a fair bit, in particular the well-known paper of Goomans and Williamson. And the other question is, how can we improve on this, again, from a computational perspective? That's the interest today. One way to improve on this is to use what are called triangle inequalities. So these are based on the observation that if I have a plus or minus 1 vector, then I can pick any vector f of the same length, and I have 3 entries that are non-zero, and these entries can be 1 or can be negative 1. So for any such choice of f, I'm going to have that the inner product of f with x is going to have norm at least 1 for the points that I'm interested in. So this is a valid inequality for the points that I'm interested in. I can rewrite it and get it down to essentially a linear inequality on the matrix X. And I have one of these, in fact, I have several of these for any choice of ijk, so of the 3 positions here in my vector f. And various combinations of plus or minus 1. When you work it all out, it turns out there's 4 times n choose 3 different conditions that pop out. Okay. And these are called triangle inequalities. And if I collect them all together, I get another relaxation, a polyhedral relaxation of the max cut problem, which is called the metric polytope. So that's met sub n in space n. And this is an object that's also been known and studied for a while. Focusing on the computational aspect, there were some experiments done by Barahona, Jünger, and Reinhold in '89 showing that optimizing over this from an LP perspective is a linear optimization problem and can be very efficiently done for sparse graphs. Okay. So now it really depends on how many edges you have in this graph. Okay. In particular, if we look at what are called spin glass problems, which arise from an application of max cut in statistical physics, if you look at 2D spin glasses, a recent paper by Pardel and Leers was able to solve for problems larger than 1,000 by 1,000, so max cut problems with more than 1,000 nodes. Okay. And more than, excuse me, 1,000,000 nodes, because it's 1,000 squared. This is your grid, and each point on the grid is a node for our problem. Okay. However, the flip side of using the LP approach is that when the density of the graph grows, the results tend to get weaker. And in general, the bounds can be fairly weak. We'll talk more about optimizing over the metric polytope in a moment. What I want to mention here is that there are other classes of inequalities that are known for the cut polytope. In particular, it doesn't have to be only 3 elements of f that are non-zero. You can have any odd number of elements of f that are plus or minus 1. And these give what are called odd clique inequalities. So you can get inequalities with 5 non-zero, coming from 5 non-zeros, 7 non-zeros, and so on. And even then, there's a lot more that's known about the cut polytope. But in general, the problem is not so much knowing facets, facet-generating inequalities or valid inequalities. It's being able to find them, find the ones that we're interested in from a computational perspective, and adding the right ones to the problem. So this is really something where there hasn't been a lot of computational experiments that have been done. In some cases, it's even theoretically hard to even find inequalities. Okay. But even when that's not the case, it's not a trivial problem from a computational perspective. What we do know how to solve is optimization over the correlation matrices, so the basic relaxation of max cut. Okay? Using 30 lines of MATLAB code that implement an interior point method just on a laptop, it's possible to solve this basic relaxation for max cut problems of up to 5,000 nodes with arbitrary objective in up to, say, half an hour or so. So this is the good part of what we can do. And then if we want to move to larger problems, we can do this using, for example, the spectral bundle method, of which, again, several of the authors are in this room. And this allows us to push, for example, to go for, these are now results for 3D grids, so 25 by 25 by 25, which gives a max cut problem of over 15,000 nodes, which, again, can be solved, the basic relaxation, in a bit less than half an hour. Okay. So we know how to solve this. We take this as a building block. Now we want to improve on the bound we get by using the basic relaxation. One idea that's been tried in different ways is to intersect the correlation matrices with the triangle inequalities. Okay. So we can optimize over just the correlation matrices, just the metric polytope, or the intersection of the two. Not surprisingly, the intersection of the two gives the best bounds of the three. One interesting message here is that optimizing just over the metric polytope, if you throw in all the inequalities and just try to solve the LP, because there's order n choose 3 of them, order n cubed of them, it's actually not an easy problem. This turns out to be an LP that gives a lot of difficulty to a solver. Okay. There's a lot of degeneracy happening. And also another thing that happens is that, in a sense, the relaxation over the metric polytope is a lot weaker than the relaxation over the correlation matrices. So if we look at these valid inequalities in the following sense, if we look at these valid inequalities that we were getting for the F transpose F XF for the triangles, in the metric polytope, you can go all the way to -3 in terms of the value that this can take, when in fact it should be at least 1. So there's a big gap to fill in here. Whereas over the correlation matrices, by positive semi-definiteness, it has to be at least 0. Okay. So there's a much smaller gap in that sense to fill when you want to tighten the relaxation. So using only the metric polytope is definitely, in general, a weak approach. But if you intersect the two, we can see that these bounds can get pretty close already to these best known cuts. These are actually not known to be optimal in this case, but in any case, the optimal cut is somewhere in between these two values. Okay. The challenge now is, okay, we can do this. We have a good way of optimizing over the correlation matrices, over the correlation intersection triangles. How can we move these bounds even closer to the gap, to the cut? Okay. That's what this talk is about. And the idea that we want to do is in the same spirit as other ideas that have been proposed before for relaxations of binary optimization problems, in the spirit of what's called the Sherali-Adams RLT procedure, the Lovász-Schreiber liftings, and also these, what I call the higher liftings that I was working on with Henry Wolkowitz at the same time that Jean Lasserre also published his paper on this topic. And also there's a more general approach by Pablo Perillo that essentially leads to the same ideas at that time. For the case of binary problems, what's nice about these approaches is that you can get the integer optimum in a finite number of liftings. Okay. That's the good news. The bad news is these liftings grow very fast. In fact, they grow, computationally speaking, way too fast. We can't really get beyond problems of about 50 nodes for max cut using any of these approaches. Certainly not the SDP-based approaches. Okay? And this is because the matrix of the SDP relaxation grows too quickly. The dimension just becomes unmanageable. So what we're looking at here is essentially a way of constructing what is in spirit like a hierarchy, but the matrix dimension is going to stay fixed at the size of the basic relaxation. So here's the idea. We're going to use this following observation here that says if you take from the n nodes in your graph, if you take any subset capital I of some cardinality k, okay, we just fix a subset of the nodes, and we look at the principal submatrix of the variable x indexed by the rows and columns in the set I. So we take a small piece of the matrix, and the key observation is that if the whole matrix is in the cut polytope for n nodes, then this small principal submatrix is in the cut polytope for the appropriate size. Okay. What this means is that if I have a matrix that's in my ideal relaxation, I can take a small piece of it, a small principal submatrix, and express it as a linear combination of the 2 to the k minus 1 cuts in this smaller cut polytope. Okay. So here are my 2 to the k minus 1 cuts with coefficients lambda, and I want to take a convex combination of that. This is essentially an exact description of this smaller cut polytope. Okay. And I can pick k as I wish, essentially between 2 and n to make things minimally interesting. So by choosing k, we get a sequence of problems that form a hierarchy in this sense. What we have is that at the kth level, we have the basic SDP relaxation. We have all the triangle inequalities, conceptually, not computationally, but conceptually we're going to put them all in. And then we have these constraints on the principal submatrices with the right size. Okay. So at one level, we would add all the 2x2s. At the next level, all the 3x3s. At the next level, all the 4x4s, and so on. The good news is that for k fixed, in theory, this is solvable in polynomial time. Okay? And if we let k depend on n, then as k approaches n, our bounds are going to get better and better. And when k gets to n, then we get the exact solution, because then we're basically optimizing over the actual cut polytope that we're interested in. Now, our objective computationally is not to get to n, but to use small sizes of k to improve the relaxation. So if you start looking at small sizes of k, one of the things to observe is that for k at most 4, the bound is not going to change. The bound with SDP and the metric polytope is not going to change by adding any of these because, in fact, for dimension up to 4, the metric polytope gives you the cut polytope. These should be k's here. So the smallest interesting case that we want to look at is k equal to 5. Okay, there's no point looking at k less than 5. Yes?
I mean, that's cut 3, right?
That's cut 3, yeah. Now, that's a good, so when you add this, for example, for 5, some of these are going to become redundant. Yeah. So what's going to happen, and that's going to come out in the computation as well, is that as we add more of these, the number of triangle inequalities is going to decrease because we're going to be able to remove some of them. But this is a conceptual relaxation. You're right. There's redundancy here. And in fact, when I put k equal to n, there's redundancy. I don't need anything else, right?
But the triangle ones are always redundant.
But we make sure that the triangle ones are always satisfied. That's what this statement means. We make sure that all the triangle inequalities are satisfied, and then we add this extra requirement on top. Does that answer the question? Or
You're only going to enforce for some subset of cardinality.
well, now we have to decide what we do. Do we put? I mean, this is defined for a single k, right? So I fix a k, and I add. Conceptually, I add all of these conditions for fixed k. Okay. But even I'll continue, and maybe that'll clarify things a bit. So here's a small example based on a max cut problem that was used by Monique Laurent in a paper in 2004. This is the objective matrix for a 7x7 for a 7-node max cut problem. And here's the bounds of the relaxations, of a bunch of relaxations. So if we look at we start with the correlation matrices, and we have a bound at 6.95. And then if we add all the metric inequalities, the bound goes down to 6.05. Then if we keep the metric inequalities and add the best of these k equal to 5, so I add one of those conditions for k equal to 5, which happens to be this particular subset, the bound drops from 6.05 to 5.98. If I add the best of the 6 cut polytopes, the bound goes down to 5.94. If I now add all the cut 5s, so I come back here, I fix k equal to 5, and I add all of these, okay, then the bound goes down to 5.8. If I add all the 6s, it goes to 5.6. And of course, if I add the 7, then I get the exact bound, because now I have the exact problem. Okay. And in here, I have the other two, the Anjos-Wolkowitz and the Lasserre second-level relaxation. Yes?
Do you explicitly add all the linear inequalities of cut 5 and cut 6 and so on?
I'll get to that in a moment. Let me just postpone. So this is to show what the impact on the bound is. Now there's the question of what do you add, right? There's some previous work that uses very similar or the same sort of inspiration ideas, which is a paper by Buchheim, Lies, and Oswald using what are called target cuts, and also another paper by Bonato and co-authors. And in both of these cases, what they do is they start with the big polytope, with the big relaxation. They project to a small space. They find valid inequalities in this projection, and then they lift them to the original problem. Okay. It's similar to what we're doing in that we're taking our big cut polytope and going to small dimensions, but instead of looking, in a sense, for an outer description, we're actually working with the exact polytope in that smaller dimension, and then lifting that up to the higher level. Okay. And it turns out that this seems to have some good algorithmic advantages compared to the other approach. Another observation is that you can think of this, at least partially, as a variant of column generation, because we have these constraints that I indicated here, where we're taking a linear combination of an exponential number of terms. Okay. But when you actually solve this, most of the lambdas most likely are going to be 0. You don't need all these terms. So this inspires the ideas of why don't we just generate these guys as we need them in terms of the optimization. So I don't know if this is the question that you had. So right now we can think in terms of adding them all, but there's a question of efficiency here that you don't necessarily have to add all these terms. And you can think of it as a column generation idea. Because you still add a fair number of variables and equations. And adding all of these subsets at once is computationally inefficient. So the challenge really is, which are the good subsets that I want to add? Okay. From a computational perspective, this is, I think, the right question to ask. And there's at least two possible ways that one can do this. One of them is to check for violated pentagonal inequalities. So these are the inequalities, the odd cycle inequalities, odd clique inequalities that I showed before, with 5 non-zeros in F. Okay. And we check because we know all the triangles are satisfied. So we have to go to the next level of these odd clique inequalities. We basically look for the most violated ones, and we add a certain number of them. Okay. And we add not the inequalities, we add the subsets of nodes corresponding to the most violated inequalities. Okay. But we use the inequalities to guide the choice. An alternative approach is to say, okay, take the current point and essentially project it onto this combination of the points of the small cut polytope, okay, and check the distance, okay, and then select the subsets for which this distance is significantly greater than 0. And in the interest of time, I'm going to show you results for the first part. If you want to see results for the second part, you can go to the poster presentation of Elspeth tomorrow afternoon. So we focus on the case k equal to 5. Basically, we solve the initial relaxation. We look for good subsets, resolve with these constraints added in, add triangles, remove inactive triangles, and then resolve and just keep repeating this process. Okay. And this is how we can make sure, we can make sure that you always stay within the metric polytope, that all the triangles are satisfied all the time. We look at instances where the C intersection met relaxation starts to get weaker, which means problems with at least 60 nodes. And we use STPT3, and we basically use this idea of the maximum violation. This is essentially, for one instance, how the computation progresses as an example. This is the bound on the correlation matrices, so this is the basic STP. This is the bound on C intersection the metric polytope. And then this is the optimal cut for this example. Okay. So what we want to do is to reduce this gap here between the two, and we see the bound going up here as we add more rounds of these constraints on subsets I. The violation, of course, is decreasing. Remember, violation is less than 1. So as we add more subsets, the ones that we add violate less and less the constraints, the inequalities that we're using to test. And while the number of these little cut polytopes goes up, the number of triangles go down because they start getting redundant, and the computational method just takes them out as necessary. And here's one table of results for graphs from 70 up to 100. Again, in fact, this is the same example that I just showed some results for, this one here. And this is the gap, the sort of the 14% is so this is the proportion of the gap between C intersection and the optimal cut that is left after we go through this process. Okay. So this means that we've closed 86% of the gap that was left after adding all the triangle inequalities. Okay. This means that we closed 64%. Here it's 72%. And here it's 36%. Okay. So as the instances get bigger, we close a bit less of the gap. But this is still a substantial improvement in terms of the bounds, and you can see it here between these columns. So there's results here for different kinds of graphs. These ones are randomly generated with a 50% density and edge weights both negative and positive. This is for the edge weights between 1 and 10, and these are dense. So again, the gap reductions are quite interesting. And then this is density 50% with weights all 0 or 1. So there are different kinds of graphs. And here, basically, the gap that's left is 0. So from C intersection N to the cut, the gap has been closed. Okay. Now, there was a very small gap to begin with, but now this actually gives us a mean to totally close it for this example. In closing, just want to mention that this whole talk was about max cut, but in principle, this can be used for other types of optimization problems where you have this property that projecting onto a smaller subset of the nodes, in this case, maintains the same structure. Okay? So that it allows us to generate this description in the smaller space and then move it back up to the big problem. So other candidate problems for this include max stable set, max clique, graph coloring, and there's probably more that are going to be added to the list. There's still lots of open questions. I don't have time to really go through all of these, but of course, one of them is how do you separate these efficiently, and how do you move to bigger sizes of these subsets? And ultimately, the objective is to develop machinery that can then be included in a general branch and bound package like BICMAC to improve the performance that we can achieve on solving general max cut problems. So that's all that I had to say. Thank you very much for your attention. Now, there were a couple of questions. I don't know if I answered them or not in the end.
So how does this compare to just going to the second lift in the hierarchy?
In few words, it's a lot cheaper because going to the second lifting is really very expensive. I mean, these are all graphs with at least 70 nodes or so. I don't think that we can get beyond 50 nodes on even just Lasserre's second lifting or even the simplification that I worked on with Henry. I remember, so 10 years ago, I could hardly solve a problem of size 40. That's probably gone up, just the relaxation, right? That's probably gone up since then, but I doubt that it's gone up by that much just because the complexity really hurts.
So how do you pick the subsets?
Yeah.
I mean, somehow that's a whole.
That's the whole key.
Yeah.
What we're doing right now, so what I explained here, these are these two things. So what I've explained here is this idea of saying I'm looking for a subset of size 5. So I look at the 5-clique inequalities. If I have a 5-clique inequality,
You have to switch for. You have to pick for which subset of size 5.
I have to pick for which subset of size 5.
Right.
So for each subset of size 5, I can look at the 16
You have into the 5
inequalities.
subsets. So how, that's what I'm asking. I mean, how do you pick which subset?
Here we just pick them at random. Here I think we just, so we do a randomized enumeration of all the subsets of size 5.
Randomized enumeration.
We just pick a subset of 5, and we check at random. And we,
Uniformly distributed.
yeah, I mean, in some kind of random number, pseudo-random number generator.
So most of them will be like in parts of the polytope that you don't care about.
That you don't get anything out of, yeah. And so there's very little here on how to actually how do you do this in a smart way. But I mean, the point is we use the violation of the 5-clique inequalities to guide the choice of the 5 subsets. These graphs are small enough that you can do this without too much difficulty. But that's a very good point. If I have a graph with 1 million nodes, then I can't start fishing around. So there's still the question of how do you pick these subsets. Yeah. Yes.
You mentioned maximum clique problems.
Yes.
I understand that you have positive weights
Um,
on the negative weights. You can solve any quadratic optimization.
Sure. Yeah. I mean, here we don't really care about the weights, but the interesting ones would be the ones where the problem itself is not.
You thought of classical max clique.
Yeah.
Cardinality.
Cardinality.
Not,
Yes.
not max weight.
Oh, I see. Okay, sorry. No, I understand what you're saying. Yeah. So here I had max clique in terms of cardinality. Yeah. But this is about approximating the convex hull of the integer points. So I don't know if the weights would.
Decomposition might be violated. If you look at
If you look at a subgraph, that might be violated in that case.
negative.
Yeah. So this is the key point is, can you do this trick of going to a smaller dimension and having the same structure? If that doesn't work, then this is not going to fly. But on the other hand, you can define this projection any way you want, conceptually, right? So as long as you can achieve something like the key observation, in principle, this all extends through. Yeah.
In your sample, you have problems with negative weights, right?
Yes.
Did you observe that the first relaxation of Domain-Williamson, you still have the ratio? Because the ratio is true for non-negative weights, right?
It's only true for non-negative weights. For negative weights, sometimes it works, sometimes it doesn't. These are the ones with some negative weights. I think it's the only one. Yeah, this is the only one with negative weights. So we'd be looking at the difference between here and here. I haven't actually computed it in this case, but here it might be violated, right? In the other tables, it will hold because the weights are all non-negative. But also, I guess, from our perspective, from the perspective of what I'm presenting here, what we're really looking at is this one here, where we already added in all the triangle inequalities, which typically is significantly, there's still a big difference between these two, and we just want to move this further, even further towards the cut. But I don't know if there'd be a way to do an approximation result on any of these.
Maybe the questions should wait because I want to talk.
And I don't want to take your time. So.